So we want to graph y equals 2 to the x as well as y equals 1/2 to the x power. We want to graph them side by side next to each other but on different coordinate planes. And we can begin by just making a table of values to see what ordered pairs are going to be on these graphs. So you might think to start just from -2 to 2, kind of your basic beginning table for our x values. And then let's just put those into our function and see what y values we get. So if we're inputting a -2 as an exponent, remember that's 2 to the -2 power, that really becomes 1 over 2 squared, which will give us 1 over 4. Remember, we're trying to make this table without using our calculator. Now input -1. 2 to the -1 power will become 1 over 2. So inputting -1 will give us 1/2. Inputting 0, 2 to the 0 power should give us 1. 2 to the first is 2. 2 squared is 4. So let's plot these points. So at -2, we're just barely above the x-axis at 1/4. At -1, we're at 1/2. At 0, we're at 1. At 1, we're at 2. And at 2, we're up at 4. Now, in fact, we could actually extend our table a bit. We could certainly input 3 for x. 2 to the 3rd power, 2 times 2 times 2. That would give me 8. So we could also plot 3, 8. And you'll notice then that as my x values get bigger, so do my y values. So when we start to connect these points, you see that we have this growth, and this function grows very quickly. That's why we call it exponential growth. But what's happening as we go to the left, as the x values get small? Right now, the smallest x value that I have in my table is -2, and that y value is a 1/4. What would happen if I went to -3, for example? So if I were to input -3, that would be 2 to the -3rd power. That's 1 over 2 cubed, which is really 1 over 8. So notice what's happening as the x value gets smaller and smaller. -3, we could do -4, -5, and so on. What's actually happening to the y value, it is getting smaller and smaller, but it's not turning negative. It's getting smaller and smaller, but approaching 0. And what that means about the exponential function is that it does level off, and it has a horizontal asymptote. It's just going to cruise along the x-axis. It's never actually going to intersect it or go below the x-axis, because we can't ever get a 0 for a y value or a negative y value. So this is our graph of y equals 2 to the x power. So now, side by side, let's compare this function with g of x, which is 1/2 to the x power. And we can go ahead and start it the same way by making a table of values. Ideally, once you make a table of values a couple of times, you won't have to make the table again. You can kind of make the table in your head, because these are our new parent functions for exponential functions. So if we put in -2, that's going to be 1/2 raised to the -2 power. Remember that negative exponent, you can think of it as 1 over 1/2. Or in this case, you can think of the numerator going to the denominator and the denominator switching to the numerator. So 1/2 to the -2 will really be the same as 2 to the 2nd, which is going to give us 4. And then trying 1/2 to the -1st power. So that's going to be the same as 2 to the 1st power, which is going to give us just 2. 1/2 to the 0 is 1, 1/2 to the 1st is 1/2, and 1/2 to the 2nd, or 1/2 squared, will be 1/4. So now let's plot these values. So -2, I'd be up at 4, -1, I'm up at 2, 0, 1, 1 1/2, and 2 1/4. So notice, I could go ahead and put some more values in my table if I wanted to. I could go ahead and go farther to the left. I could input, say, -3 for x. And if I did, I'd end up with 1/2 to the negative third power, which would turn into 2 to the third power, so I'd be up at positive 8. So you could plot the point -3 up 8. So you'll notice that what's happening on this function is as we go to the left, that's where the y values are growing, growing, and growing. However, as I go to the right, now my y values are getting smaller, but they are leveling off and again approaching 0. So this is what we call our classic exponential decay graph. Here on the left you have exponential growth, and on the right you have exponential decay. So what do these two graphs have in common? Well, the first thing to notice, if you take a look at the table, is they have one point in common on both of the graphs. They both contain the point 0, 1. So a commonality is that the y-intercept is 1. Another commonality is the domain for both of these graphs. You'll notice that both graphs extend to the left and to the right forever. So each graph has a domain of all real numbers. You also should be able to figure out the domain not just from the graph, but also by looking at the original function and then just asking yourself, what are you allowed to substitute in place of x? What kind of numbers can x be? Well, x is in the exponent, and you can have any type of number in an exponent. That supports why your domain should be all real numbers. Next, the range is actually the same for both of these graphs. So the lowest to the highest, we say that the range would be from 0 to infinity, but it can't actually touch 0 in this case. 0 is a horizontal asymptote, and for these functions, it cannot be crossed or it cannot be intersected. And that's because there's no way for us to put in an x value that's in the exponent to get an output or a y value of 0. So 3 commonalities so far. They have the same y-intercept, they have the same domain, and they have the same range. And then the last commonality is that both of these graphs have a horizontal asymptote. And in fact, they have the same horizontal asymptote. Both the exponential growth and the exponential decay models have a horizontal asymptote of y equals 0. And that would be our 4th commonality. Now, how do you determine whether or not the function is an example of growth versus decay? Well, it's easy to kind of just look at the graph, and as you read it from left to right, look at your y values. Are they growing or are they getting smaller? But we actually want to be able to determine whether it's growth or decay from the original function. So determining whether or not the original function is growth or decay really requires us to take a look at the base. In my first parent function, it was y equals 2 to the x. And this base value, of course, it is a positive number. It has to be positive in order for it to be an exponential function at all. However, the base here is a value greater than 1. So when the base value is greater than 1, that's how we know we have an exponential growth scenario. Whereas for g of x, the base value is a fraction. Specifically, not just any fraction, but this base is a fraction that is greater than 0 and smaller than 1. It's a fraction in between 0 and 1. And that's how you can tell by looking at the function that this is going to be an exponential decay function. Now, these are just 2 of the common exponential functions. The base doesn't have to be a 2 or a 1/2. You could have a base of 3 or 1/3 or 2/3 or 5/4. Remember that the 2 restrictions on the base is that it has to be a positive number and it can't equal 1. Other than that, you can have any positive base value other than 1, and it will be an exponential function. It'll be either exponential growth or exponential decay when you take a look at the parent function.